People are waiting in the lobby. Keshav, can you hear me?
Yes, sir, I am able to.
It is showing you are waiting in the lobby. I don't know.
No, actually, when I joined first, it was showing meeting is not started. So
Ah,
I have left the call again and joined.
okay, good, good. So you guys are understanding concepts, right? You feel good about the course, or what is the feeling so far?
Yeah, it is understandable, sir. But it's too much of content, and especially I am unable to spend time. That's where it is. That's where I am. But it is understandable.
Okay, okay. So, but
I'm
no,
able to follow.
don't delay things, right? As soon as possible, start working on deep learning. Okay.
Yeah,
And if you have questions, right, we are anyway here, right? So to help you. So Keshwa is there and I am there. So we'll help you.
sure, sir. Thank
So thank you. So no, convolution, right? What is convolution? Element wise multiplication. The outcome of the element wise multiplication is called as convolution, right? New matrix. When you take this two-dimensional matrix and apply onto this matrix, you get a new matrix. This is called as convolution. Edge detection is the main goal, and there will be, if any picture you take is going to have many edges, and if a neural network can understand different filters or different edge detectors, right? So in an image you may have 10 edges, 10 different kinds of edges. So you need to have 10 different filters. Okay, so each filter will have its own numbers, which will actually generate a pattern like this. It may not be exactly like this, but this is an example. So it's a vertical edge filter, which is actually trying to understand vertical division between our where the shade is changing. That's what it actually found. Okay, so like that, manually finding them is difficult. Okay, so automatically neural network finding them is easy. That is convolutional neural network. Okay, so the next point is, if you have n by n matrix and you are applying f by f filter, you will get an outcome of n minus f plus 1 by n minus f plus 1. The 6 by 6 matrix, you applied 3 by 3 filter, you got 6 minus 3 plus 1, 4 by 4 matrix. See this here? See, on a 6 by 6 matrix, you applied 3 by 3 filter. N by n matrix, f by f filter, you get n minus f plus 1. Okay, this is called as valid convolution, where you did not do any manipulations. Directly, you applied this filter. Okay, I'll talk about manipulations a little bit. So what happens is, the drawback with convolution neural network is it shrinks, it reduces the dimensionality, but over a period of time, right, it may damage the image also, shrinking the output. So every time we apply this operation, the image shrinks, right? If 6 by 6 image became 4 by 4. When we apply the operation multiple times, there is a danger of losing the image completely. Right? It may become a one pixel or 2 pixel, whatever. Right? That is one disadvantage. Second disadvantage is, no pixels on the edge are used less, are not used many times. If you look at this convolution, right? First it applied here, then it slided, then it slided, right? And then it came to, it would have came to this place. Right? The next convolution would have been applied here. That means this 10, this cell, is considered only once. When we calculated this convolution, only once it was considered. Right? The other tens, right? These two tens may have been considered twice. Right? Here it considered. When it went down, it got considered. When it got down, it considered. So other tens, right, in the edge got considered only twice. But if you take the tens in the middle, right, they would have been considered more number of times. Suppose that in a picture, the desired object, whatever you are trying to identify, is at the edge of the image, the convolutional neural network will not be able to identify. Got the analogy? Pixels at the edge are not considered quite frequently, are used less. The disadvantage is that if some object you are trying to identify is at the edge of the picture, your what you call it as convolutional neural network is not extracting the essence from that edge. In a way, it is not using the pixels many times, right? So that's going to damage the understanding. Okay, these two are the disadvantages. Any questions on the disadvantages? We'll have solutions for that, but any questions? Okay. So we can actually do padding to avoid these two problems, damaging the image or reducing the dimensionality too much, and ignoring the edge pixels. See, this is called as padding. What we did, we added one zero, row and column here. Here one row, and one column we added zeros. This is called as padding. Now now if you apply the filter, right, it's going to be n plus 2p minus f plus 1 by n plus 2p minus f plus 1. What is p here? The number of paddings added. Right, this is one padding. This is called as one padding. If you say two padding, right, you will get one more layer. Okay, and then this is 2 into 1. 6 plus 2 into 1 minus 3 plus 1 is 6 by 6. I added one padding to 6 by 6. I applied 3 by 3 filter. I got a 6 by 6 output. See this image? No, image dimensionality did not get affected. Okay, one more advantage is, if you look at the convolution, it starts here, it applies here, and then applies here. Let me take a screenshot and explain. Maybe this is Windows, right? It will be easier to take screenshots. Give me one second. My voice is clear and audible, right?
Yes, sir.
So so here, right, when we apply the convolution now, it will actually apply like that. It's a 3 by 3 filter. So first it will calculate all these, linear combination of all these numbers. The numbers in the filter are random numbers and they get calculated, right? Again, like that. Right? And like that it will move, and then it will come down and do like that. Right, like that. So what happened? This pixel was considered 4 times. Right, first time when it actually calculated linear combination there, second time when there, right, third time there, fourth time there, right, yeah, that's it. This was considered 4 times. When the padding was not there, it was considered only once. But when we added padding, right, it considered, so edge pixels will be considered more number of times when you do padding. That is one advantage of padding. The second thing is the dimensionality is not reducing. A 6 by 6 image, if you apply 3 by 3, it would have come down to 4 by 4. But because of this additional padding, we have got 6 by 6 matrix only. So these formulas, right, remembering them is better, because you will get, you need to actually think. It is like weights, right, in the deep neural network, how many weights are going to be there, or what is the size of the matrix and all that, where we were remembering, or we are actually logically thinking, right? That actually gives you a little bit intuition of how the network is going to move, right? These are all black boxes when we don't focus on the formulas. While practicing initially, we should actually think about these, and maybe take a pen and paper and try to calculate a little bit as aside while doing the network, right? So that way you'll get more clarity, or it will be more like a known thing, right? Generally the world is not known. We don't know why many things are happening, but because of getting used to it many times, we think that it is kind of known, right? Like that we'll create a feeling. When you are confident, right, you can do. Maybe clarity is less, but confidence will give you, a way to move forward, right? May not be good, but that's how it is. The neural network is a black box. Within that whole thing, Exactly what is happening, nobody knows. But at a high level, how weights get calculated, how the network is moving, we know. We can actually do whatever. It's like the world only. Okay. So any questions here on the formula or any other thing?
So where are we applying the padding?
Yeah, I'll show you. You know, in the neural network, right? You have parameters in CNN, Con 1D, Con 2D are the classes. In that class, you can specify padding.
No. Why are we actually? Why do we need to apply padding?
First problem, when you apply, you know, when you don't apply padding, this pixel was considered only once while doing linear combination. Okay?
Yeah.
Understood? Huh?
Yeah.
So when we are not considering the edge pixels more number of times, if the image which we are actually trying to identify is present at the edge, right, the pattern will not be understood properly. When you do padding, right, this was considered 4 times. So if you add one more padding, right, this will be considered more number of times. If you want, you know, the pictures we are working with have got, you know, important things on the edges, then you add padding. That is one reason. So the second reason is you have a huge neural network, maybe, you know, 10 layers or, you know, 20 layers. And by the time the neural network reaches 20th layer, right, the dimensionality of the picture may come down to 1 pixel or 2 pixels, because every time you apply neural network, it is the dimensionality is reducing, right? Right? Every time you apply a neural network, the dimensionality is reducing, right?
Yeah.
So
Yes.
by the time it reaches 20th, you know, again you applied 3 by 3 filter, again 3 by 3 filter. If you apply 3 by 3 filter on this, right, what happens? 4 minus 3 plus 1, right? 4 minus 3 plus 1 is 2. It will become a 2 by 2 matrix. Right? If you apply one more time, you know, one dimensional pixel or two dimensional pixel, filter, it will become a one dimensional one. So a 6 by 6, 36 pixels, you reduce it to 1 pixel, that means total image would have gone. Right? In the process of understanding pattern, you may damage the picture, right? So to not to damage the picture while understanding the pattern, you have to add padding. Okay, got it? In a huge neural network, if you don't want to damage the picture or n number of layers, you add padding. That is one reason. Second reason, edge has got important things, then also you add padding. Okay, that's the reason.
Yeah, sir.
Yeah.
The pixels of the picture may not be n by n, right? It will be n by m.
Yeah, n by m, but we'll actually take n by n. You know, in a way, we try to eliminate some of the, you know, uneven columns or rows. Suppose that you have, you know, 102 pixels in a picture. You take 10 by 10 matrix only. Those 2 pixels will ignore.
Okay.
It will not damage, because, you know, generally pictures will have 400 by 400 by 3 or maybe 800 by 800 by 3. That means, like, you know, 48,000 pixels you will have. In those 48,000, if you ignore 100 or 200 pixels, it's not going to damage. Even 1,000 pixels you ignore, it's not going to damage anything. Maybe edge will get cut, you know, chopped off.
Yeah, if the edges get chopped up, then won't it be a problem?
It will be a problem if the pictures have got images in the edge. Generally, what we do is, you know, we collect data, right? You know, if you take our speed detection system, right, we collected data in the way we wanted, right? Every project, right, needs to collect data, label data. That is for sure. You know, with the current technological whatever capabilities, we need to collect data. While collecting data, we will not collect data which is going to, you know, fall on the edge, right? So that way it is okay. Got it?
Yeah, yes.
Okay. So definitely, you know, because, you know, maybe after 5 years we'll have data for everything. Maybe that time the data may not be as we expected, right? So what we do is in that case also we'll collect maybe 100, 200 records and then try to use transfer learning. Already trained model we'll take and then do transfer learning. And so anytime we have to collect data, we have to label data. If nobody, if somebody doesn't know we have to collect data and label data, they'll try to propose some things which are based on the existing modules, existing pre-trained modules. Pre-trained modules will not work on our data. Most of the cases, pre-trained models will not work on our data. So we'll collect data. While collecting data, we'll carefully collect it. Even when we ignore some pixels, it's going to be okay. Okay.
Sir, is there any way to like find out what is the filter we need to give here? 3 into 3 or 4 into 4? How do you know that, sir?
That's a hyperparameter, and like number of layers, number of nodes, right? Filter size is another hyperparameter.
Okay.
We need to play with it, right? We need to manually play with it first and see how the model is working. Then you should use grid set CV. I've shown you that, right? And put them and then try to run it and it will find.
Yes, sir. Because if we are giving the filter size 2 into 2, then we will not get the same like output, sir. Means like
Yes, sir.
6 output, right?
Yes, sir. Yes. 6 by 6 will not be there. If it is 2 by 2, right? Here 3 in place of 3 you will get 2. So that's going to be 7 by 7 you get. It will increase. That's called as upscaling and downscaling. And this is downscaling. Basically, when you do a filter and the image is getting reduced, it is called as downscaling. Whatever the scenario you spoke is called as upscaling. Upscaling is also useful. What we do is, right, there is a auto decoders, auto encoders is an interesting topic. I'll talk about it, just briefly now, and maybe future, right, we'll actually understand it better. So what is auto decoder, auto encoder is, suppose that there is a picture of a person, right? There is a picture of a person. Okay. You passed it to a CNN network. Okay. There is a higher dimensionality. You applied filter, it reduced. You applied filter, it reduced. You applied filter, maybe it became a vector at one point in time. What you do is you try to produce the same picture by upscaling it. Right? The same picture you take X and Y same, the same image. Okay. You take the image, you downscale it, you upscale it, right? You try to reproduce the same image. In this process, right, the algorithm is actually learning this particular vector that can be used to represent this person. This person's pixels may be 48,000, right? You try to downscale it and upscale it, right? When at one point in time, the difference between the X and the generated X, right? X cap, I'll say. X and the generated X may be less. Error is less. That means what? This can be used to represent this picture. So this is called as auto decoder and auto encoder. This is encoding. This is decoding. Right? We are encoding the picture into a vector. We are decoding that picture into the same picture. So this is called as auto encoder and auto decoder. Okay. So in this process, right, the filter size actually matters. You take a filter size that actually reduces the picture to some extent, and then you take filter sizes in such a way that you add padding around this, and then try to apply filters in such a way that it actually raises. Got it?
Yes, sir.
So we'll see that also. We'll see that.
Encoded, so the encoded output may not be a vector. It could be a reduced matrix type, right?
It can be a matrix. It can be a vector. You can actually do ravel or flatten on a matrix. It becomes a vector, and then again you reshape it. It becomes a matrix, right? So it's kind of back and forth. We can generally I say vector because at one point in time, right, we try to convert words into vectors and pictures into vectors and then try to in face detection, right? One shot learning is a process where you try to convert picture into vector and then try to use those vectors, the Euclidean distance, cosine similarities, to see whether the same person is in the database or not. Yeah, that's another project. Maybe if somebody is interested in computer vision, right, they can do. Okay. So this is a very interesting concept. Actually, Narayan, you asked a right question, and the number of the padding and the filter size actually determines whether we are downscaling or upscaling the image. Okay. So any other questions? So this is the downscaling, upscaling. This thing is kind of unsupervised way, but again it is supervised, right? In deep learning, that's the advantage. If you take a PCA, you don't know where you are going. You just apply, the principal component. It extracts the explained variance ratio. We don't know whether variance ratio is the thing which is determining the image or not. But here you are sure that you are trying to damage this and reproduce it. Right? When it is able to reproduce it, the damage is what you can use to represent the particular picture. That's an intelligent whatever. This is the basis for GAN, generative adversarial network. This is the basis. This is the beginning of GAN. Okay, if you understand auto decoders, auto encoders, right? If you read GAN, right, you can actually do it. That's not a big deal. Whatever we are covering is kind of 99% in all aspects. The rest is whatever is found is on top of whatever we are learning here. Okay, either it is machine learning or deep learning. Okay, I'll cover, but in case time is not sufficient, I'm just trying to play safe, but I'll not actually escape things. Okay, so this is so the next thing is valid and same padding. This is the keywords we need to remember, right? When I say valid padding, why am I saying in Conv2D and Conv3D APIs, right? In a TensorFlow, let me try to show you that. We'll see Conv2D first, two-dimensional convolution. In this, see this padding, it's a parameter. It has got two values. It will take two values, valid and same. This is again a confusing thing. I'll show you in a moment. Padding, sorry, valid and same. What is valid? You take n by n matrix and apply f by f filter, and you get n minus f plus 1 by n minus f plus 1 output. This is called as valid padding. No padding at all. Zero padding is called as valid padding. Okay. Same padding. Same padding means you pass n by n matrix, you should get n by n output. You actually take n by n matrix, you apply f by f filter, the output should be n by n matrix. So padding will be decided by the model, and the padding is going to be calculated like this. P is equal to f minus 1 by 2. If P is 3 by 3, sorry, if the filter size is 3 by 3, the padding is going to be 3 minus 1. 2 by 2 is 1. 1 padding. Any matrix you take, you apply 1 padding on a 3 by 3, 3 by 3 filter, you will get n by n output. Okay. If it is 4 by 4, right, the filter size is 4 by 4. It's going to be 4 minus 1, 3 by 2. It doesn't know what to do, or maybe it will take 1. That's where the filters are always going to be odd number. Okay, 5 by 5 will take 3 by 3 or 5 by 5. 5 by 5 means 5 minus 2. 2 by 2 means 4 by 2 means 2. Right? Padding is going to be 2. If it is a 5 by 5 filter, whatever dimensionality the n by n matrix is, right? You apply 5 by 5 filter. You want to get 5 by 5, sorry, n by n output. You need to apply 2 padding. Got it? Whether I should be applying 0 padding or 1 padding or 2 padding to generate the same dimensional matrix can be calculated like this. There is no need for you to calculate it. If you say same in this class, right, while instantiating the Conv2D, if you specify padding is equal to same, it will internally calculate that. It will internally calculate that and use it. Got it? Got it?
Yes, sir.
Instead of doing that, you can specify the padding also. Padding is equal to 3. If you say 3 by 3, it will take. Padding is equal to 5, it will take 5 by 5. Okay. You can actually give a number also. So let us look at that API. So valid or same results in padding left out. I think yeah, valid padding is what actually makes the filter size. Say there is filter somewhere. Do you see filter here? Yeah, filters. Right, filter dimensionality. If you say integer 3, that means 3 by 3. 5, 5 by 5. Right? But should I be adding padding or not? Is valid and same. If I say valid and then say integer 5, right? It will upscale or downscale, it doesn't matter. It will just do it. Okay. So you can specify the, I think padding number also you can specify. Person padding and same data format. Yeah, I think that is sufficient. We'll think about it later. It's sufficient. Okay, so that is no valid and same. Valid means no padding. Same means whatever input you give, the same output should come. There is another concept called as stride. Okay, so these are all hyperparameters in our the convolutional neural network. Stride. Right? Stride is another hyperparameter. So what is stride? Initially, when we looked at the convolutional movement, right? It started here, moved a little bit, right? Moved a little bit. It is moving one column at a time, right? That means stride is equal to 1. This is stride is equal to 1. It moved one column, one column, one column. Again, one row it will move. Again, one column, one column, one column. Again, one row it will move. One column, one column. Like that, it will calculate. Okay, that is stride 1. Okay, stride 2 means it will actually jump 2 columns. See this here? Started here, it jumped, 2 columns, and then 2 columns in the sense it is skipping these 2 and then starting here, right? So like that. Stride 2, stride. Why stride is needed? If the picture is too dense with pixels, and we wanted to experiment, do we want all the pixels to be considered, or some pixels can be ignored? Right? So if you do stride is equal to 2 or 3, right? The pixel consideration is going to be less, right? So when compared to 1, the linear combination calculation is going to be less, right? So it's another hyperparameter. Okay, you why do you want to ignore some pixels, or number of times you calculate linear combination? Why do you want to ignore? There is no reason there, right? It's a hyperparameter, and you play with it and find it out. Got it? Stride, did you get it?
So will it impact the dimensions of the output after applying the filter?
Yes, and really, it will definitely impact. I'll show you the formula. Right? See this? This is a stride formula. When you apply stride, right? If you don't have stride, S is equal to 1, right? S is equal to 1 means n plus 2p minus f plus 1, right? If S is there, n plus 2p minus f, so f by s plus 1. So dimensionality reduces drastically. Kind of multiples of this 2, it will reduce. Multiples of the stride, it will reduce. The same, I have taken 7 by 7, picture and 3 by 3 filter, and stride is 2, it actually became 3 by 3. The dimensionality reduces faster. The picture is too big, you don't want to, you don't want to have too many layers, and you want to, quickly reduce the picture to lower dimensionality, you apply stride also. Got it? So, the outcome is a fraction, right? It will actually takes floor. It's 1.5 or 1.6, it takes 1. Okay, it is 2.0, 2.1, it takes 2, something like that. So floor of the number it takes, right? Okay, good, right? Can I move on? Okay, now the actual convolutional neural network we are looking into. Till now, right, we looked into just the theoretical part. So suppose when you take a color picture, the color picture will always have pixels related to red channel, pixels related to green channel, and pixels related to blue channel there. Okay, and one more point I need to explain. There are three kinds of pictures: grayscale image, binary image, and color picture. Binary image means all the pixels in the image will have 0 or 1. Either 0 or 1, that's it. It is called as binary picture. Okay. Grayscale image means all the pixels in the image will have a range between 0 and 255. Any pixel you pick, it's going to be between 0 and 255. That is grayscale image. Okay. Color picture means there will be 3 channels. In each channel, there will be numbers between 0 and 255. Here, there will be numbers between 0 and 255. In this matrix, also 0 and 255. Here also 0 and 255. When you combine all three, 0 and 255 colors, right, you get a color picture: red, green, and blue. Okay, those are three different kinds of pictures: binary, grayscale, and color. Any questions? Good. Right?
Grayscale has only one channel and color has three
Grayscale.
channels. That's
Binary and grayscale will have only one channel. That's a good point. Color will have 3 channels.
yeah, the number of pixels in each channel is 256 in grayscale or color.
Yes, sir. Grayscale means you actually convert this 3-dimensional matrix into 2-dimensional matrix. That becomes grayscale. Right? You ignore the channels and corresponding numbers, corresponding whatever. Right? It becomes a grayscale image. Okay, you want to convert a color picture into binary image, right? You convert this into a square matrix and replace all greater than 0 numbers into 1, all zeros. That's it. That's going to become binary image. Why do you need that? In some cases, right? If you take number plate recognition, you take the picture and it may have some stickerings and all that on it. You convert it to grayscale, it becomes more clear. And there are, in OpenCV, there are concepts. I'll talk about them tomorrow. I need to, remind myself of those terminology. Right? I'll look into that and explain that. Okay. So you apply using OpenCV, you try to do some curation of the picture. That way it becomes more clear. And then you apply the algorithm to extract the numbers. Right? OCR, you need to do these pre-processing tasks on, on documents before you do OCR. But OCR is not perfect. It will not be able to extract everything, right. I'll show you an example maybe after. Yeah. So when your picture is having 3 channels, right? These are called as channels: red channel, green channel, and a blue channel. Okay. So in our NumPy array, do you see the dimensionality like this? A 3-dimensional matrix. Are the dimensionals are like this or in a different way in NumPy array? In NumPy array, if I have to represent this matrix, will I be representing it like this or something else?
I think it will be 3 by 6 by 6.
Yes, and very good. 3 by 6 by 6. NumPy channels first. Okay. It is channels first. So NumPy by default is channels first. That is one confusion. Right? Generally in mathematics, matrices we represent like this. But in NumPy it represents 3 by 6 by 6. First depth, then the 6 by 6 is the rows and columns. Depth and rows and columns. And if you have 4 by 4 matrix, right? That 4 by 4 dimensionality first, then the 3 by 6 by 6, this kind of boxes will be multiple of them. Okay. So that is some theory there. And when you are applying, I showed you that here the filters is an integer, right? When you say 3 on this particular picture, right? If you say 3, it is a 3 by 3 filter. You no need to specify the number of channels. Channels will automatically get created. Okay. You took this picture, you are trying to do convolutional neural network, you specified filter size is equal to 3, that means 3 by 3 matrix, right? And then channels will be automatically chosen. This 3 will actually match. Okay, the convolutional neural network will look at the previous layer's number of channels and take that many number of channels in the filter also. This is filter, right? Now how the calculation will happen? How the calculation will happen is this number will multiply this number. I think I should take another color. Maybe non-yellow. This number will multiply this number. This number will multiply this number. This number, this number. Right? This is our linear combination, right? Linear combination, right? That will multiply like that. In this channel, right? Again, this number will multiply this number. This number, right? And again, second row, third row, like, they'll all get multiplied in the blue one. Again, this number will multiply these three, and down below numbers will multiply down below numbers. That way, it's going to be a cube. Previously, when the image was a two-dimensional image, right, it was just a square matrix, right, multiplication. So now it is a cube. It is a cube and it gets multiplied, and you get a linear combination of all these numbers. So here 3 by 3 is 9, 9 and 9. 27 terms will be there in the linear combination, and you get one number. Out of all those, you get one number. Got it? That is first operation of the convolution. The first point is number of channels will be decided. You need to specify the filter size. That's it. If you say 3 by 3, channels will be automatically taken. And then when you do convolutional neural network, it does a cubical calculation, the linear combination, and generates one number only. Got it? Any questions there? Okay. So the next slide is going to be here. Let me take another.
Sir,
Yeah.
sir, in the filter,
Hmm.
so there are 3 layers, right? In each layer, the same filter will be taken.
Each layer same filter. Each layer.
No, in the filter, sir. In the filters,
uh,
we have a 3 by 3 filter, but
Ah.
with 3 dimensions.
No, they are all random numbers. Those 27 numbers are going to be random numbers.
Okay.
So each filter will have its own numbers. Right? Again, it will slide like that. Okay. Again, it will slide like that. Right? Like that, it is going to slide. Slide through it and calculate this number, this number, this number. So when on a three-dimensional picture, you apply a three-dimensional filter, you get a two-dimensional array as the output. This point is very important. And formula will not change. N minus F plus 1, because N is the dimensionality of the picture, right? F is the dimensionality of the filter. NC are the number of channels are same, so no need to consider. N minus F plus 1 is the formula to identify to calculate the output matrix dimensionality. Got it? Got it? Any questions? Good, right? Now, how it works in a neural network, right? So I took two filters. So I have a picture with 3 channels, right? 6 by 6 by 3, and I took two filters. What happens? When I took two filters, what happens? Now I specified filter size as 3 and number of filters as 2. I said, right? Do we have parameters for that? Yes, we have. Okay, I'll show you in the code, right? So 2 filters I said. So the channels will be automatically taken. First one will get 3 channels. Second one also will get 3 channels, because in the image we have 3 channels. Right? So it is going to apply. This is going to apply onto the picture, and you get a 2-dimensional matrix. This is going to get apply onto the picture and you get a 2-dimensional matrix. You add bias term now, right? After doing linear combination, you do bias term, right? So this is going to be a linear combination plus b, theta 0 plus theta 1 x1 plus theta 2 x2 and so on, theta 27 x27. X27 is going to be here somewhere in the blue, bottom corner is going to be 27. Right? Again here also, right? Theta 0 beta b1 plus theta 1 x1 plus theta 2 x2 and so on, theta 27 x27. Like that, right? When you apply the filters, you apply n number of filters, you get n number of 2-dimensional matrices. You put them into a row and then you get a. So what is it doing basically? If suppose that this is horizontal edge detector and this is a vertical edge detector, suppose that, right? If this filter took responsibility of doing horizontal edge detection, this filter took responsibility of vertical edge detection, you will get a horizontal pattern here and vertical pattern on the second output. So if you apply 10 filters of different edge detections, you will get 10 outcomes here, right? It's going to become 4 by 4 by 10. Got it? You see, ReLU, the non-linear function, is applied after the linear combination. If the linear combination is calculated, then you apply, ReLU or logistic or whatever. Got it? Any questions there? This is how in the network it works.
So the 4 by 4 matrix plus the bias will be converted into a single linear combination.
Yes, only.
Only
So
single linear.
this is broadcasting, right? This is the matrix, and you are adding B1. That means it gets added to all the cells, right?
Yeah, but what the each cell contains in 4 by 4? It's only a value, right?
4 by 4 matrix it is.
Yeah. But each cell of the 4 by 4 matrix is a number or is a linear combination?
Number only. Linear combination means number only, right? So when I say linear combination, in real time, when the network is running, these are numbers, right? These thetas are numbers, randomly chosen numbers in the initial iteration, and then afterwards it is going to be w is equal to w minus theta into the slope of the derivative. W is equal to w minus theta into, like, again gradient descent only. They get adjusted. They are numbers only.
So each cell is a linear combination.
Yes, sir.
When the linear combination is evaluated, it will become a number.
Yes, sir. Yes.
Okay. So this linear combination,
We are passing it to ReLU. Bottom line is that we are calculating linear combination and passing it to non-linear function and calculating the values. In a deep neural network, these are all actually, a 4 by 4 means 16 numbers are being outputted as a vector. But here in a convolutional neural network, it is getting generated as a matrix. Got it?
Yes, sir. So,
but major difference there and here is, if you have 6 by 6 by 3, that means 36 into 3 is 90 plus so 108, right? There will be 108 weights multiplying 108 numbers, linear combination, plus 109, and then pass it to ReLU. But here we are splitting the understanding into multiple filters, multiple weight filters, 27 instead of 109. We have taken 27 different weights, 27 different weights, 27. If we take 3 filters, right, it's going to be or 2 filters or 1 filter only, it's going to be less number of weights, trying to understand the pattern. And localized pattern it is trying to understand. On a deep neural network, as a whole, it is trying to understand linear combination. But in a convolutional neural network, this will actually get applied only this area first. Slide. Localized. It is trying to understand localized features. of the picture or text. We'll look at text in coming, maybe in 2 days. But on a picture, it is trying to identify localized patterns and
Yeah.
combine them.
So, sir, the 4 by 4 plus V1 is actually an input. So the initial input n by n into NC is actually converted into 4 by 4.
Yeah, avunandi.
Before applying the network.
Relu.
ReLU.
Yeah.
So when we apply ReLU on 4 by 4 plus V1, so we get 4 by 4 into 2.
Because this is one ReLU, this is another ReLU, right? It is a matrix, right? And you apply ReLU gets applied to this cell, this cell, this cell. Individually, it gets applied. It will see whether it is greater than or equal to 0 or not, greater than or equal to 0 or not, greater than or equal to. If it is not greater than 0 or equal to 0, it will take the 0. If not, it will take the value. It will take the value. It will take the value like that.
Okay, so can we assume this last 4 by 2 has 2 nodes in the hidden layer, the second hidden layer, or maybe first hidden layer?
Outcome of the nodes here, I think there is no node concept here, right? It's like in a convolutional neural network, filters are the kind of nodes, or filters are the kind of weights. I don't know whether we should be saying nodes or not, but it's an outcome, right? When you applied these filters, you got an outcome. Yeah, maybe these filters we can say as nodes because they are internally applying this ReLU, right? After calculating the convolution, it is applying this ReLU function. That means these are kind of nodes, right? In deep learning, deep neural network, we are applying, we are calculating linear combination of applying the activation function. There we are calling them as neurons or nodes, right? Here also we can call these as nodes, the filters as nodes. But that is outcome. 4 by 4 by 2 is outcome. Okay,
Sir,
right?
sir, if you are applying the multiple filters, the filters should have the same dimension, sir?
It will have same dimension. There is no way that you can actually specify different dimensions filters.
Okay.
You can specify filter size and number of filters. That's it. It will automatically take number of filters, and channels also you cannot specify. It will dynamically take the channels of the previous layer. How many channels are there? It will dynamically take it. There is no control over it.
Okay.
So in the previous discussion, maybe I was assuming like the filters are applied one after the other. Let's say the first one is n by nc. The first filter is applied. On the output of that first filter, we are applying the second filter. Is it not like that? Yeah.
No, they'll get applied simultaneously, or parallel or simultaneous, but they'll all be combined like this.
Yeah. Like we discussed, like when we apply the filters in multiple steps, the dimensionality may reduce to a vector, one dimension.
Yeah.
But
That is in different layers. That is in different layers. This is in one layer. This is in one layer. We are taking two filters.
Okay, so if at all, if we need to add the filters in one more layer, we will apply the filters on 4 by 4 by 2. The final
4 by
output.
4 by 2. Yeah. And they this is one layer. This is. Yeah, that's a point. I should have explained. Okay.
Sir, one more question. After filter, you showed 4 by 4 matrix for both on the top and bottom. So
Yes.
when we multiply this the 6 by 6 matrix with the 3 by 3 by 3, we should get a three-dimensional matrix, right?
No. No. You are so we are not doing matrix multiplication. We are doing element wise multiplication, right?
Okay, yeah, even element wise also, because it's there, it's a three-dimensionality is there for both the filter and also on the input. Then we just got 4x4 2D matrix. How is that? How is that calculated?
Let me show you this. See this here? There are 27 numbers here, right? In the filter.
Correct.
If you want to take 27 numbers, right? That is the area, right? That's the area. From red channel, I'll take 3 by 3. From green channel, I'll take 3 by 3. And blue channel, I'll take 3 by 3. Right? There are 27 numbers here, right? I am multiplying these 27 with those 27 and calculating linear combination and putting it here. Okay. That is first step. Second step is,
then it gives 27 values, right? Total.
yeah, it is using 27 values only.
But in 4x4, there are only 16 values.
That's what I am telling you. When you actually take 27 numbers and multiply them with 27 numbers and sum it, how many numbers you get?
One number.
One number, right? You kept it here. Okay.
Okay.
Again 27. You take the same 27 numbers and multiply with another 27. Right? Slide it and do 27. You get one more number. You slide it and multiply, you get one more number. Like that, right? When you slide downward, right, again you will get that number. So when you calculate, you take a matrix and try to do that, you will get 4 by 4 only.
Okay, got it.
Maybe if we think like it's a three-dimensional matrix and you have to do matrix multiplication, it's going to be complex, definitely. But it's an element-wise multiplication.
Okay.
So I think we have to take an example and play with it. Then you will understand what I'm actually trying to say. Got it? Okay. So this is the neural network now, and I'll show you the code also maybe. Right. So I've taken 39 by 39 by 3 image, and I said the filter size is equal to 3. Right? What is the dimensionality of the filter? If I say filter size is equal to 3 in the first layer, what is the dimensionality of the filter?
1 by 1 by 3.
3 by 3 by 3. F is equal to 3 means filter size 3 means 3 by 3 by 3, because the 3 is large number of channels. Okay, and padding 0 I said, stride is equal to 1, and number of filters 10 I said. Okay, so if I apply 10 filters, right, I'll get 10 outcomes. If I do 39 by 39 by 3, if I apply filter, let me calculate it and show. So here n is equal to 39. N is equal to 39. Let me take another color. So n is equal to 39. Right? F is equal to 3. Right? NC is equal to, this is NC, right? NC, number of channels. And then padding is equal to 0 and S is equal to 1. That means what is the output dimensionality? N minus F plus 1. Right? So it is going to be 39 minus 3 plus 1. It's going to be 37. Right? 37 by 37 is the output. Right? For each filter, you will get a 37 by 37 two-dimensional matrix. When you apply 10 filters, right? For each filter, you will get one 2 by 2 matrix. 37 by 37 matrix like that. So it's going to be 10. Right? So in this particular outcome, after applying this many filters, you get 37 by 37 by 10. This matrix dimensionality. Now I said F is equal to 5. What is the dimensionality of the filter? Here I said 3 by 3 by 3, because number of channels in the previous layer is 3. I said 3. But here, what is the dimensionality of the filter? 5 by
5 by 10.
5 by 10. 10, because here we have 10, right? And then you apply, you have stride also here. It's going to be n plus 2p minus f by s plus 1, right? So n is 37 plus 0 minus f is 5 divided by s is 2, and 32 by 2 is 16 plus 1 17. 17 by 17 by 20, because 20 filters are applied, right? F is equal to 5, whatever. And then I flattened it and then applied the dense layer. Then DNN again. Okay, that's a neural network. It is actually reducing dimensionality by looking at the target variable or the cast function. So it is a supervised dimensionality reduction we applied till here, and then we did a classification model. Okay, if you damage the image too much, the model may not work well. If you keep the essence intact, right, the model will work. So when a CNN DNN layer is not working well, you should actually look at how the dimensionality is being reduced. Summary will give you the clarity on that. Okay, so let me show you the code to build a simple neural network. I may not run it, because this is a Windows
Okay,
machine.
sir, one second, sir.
Yeah.
So the last steps I did not understand. The convolution layer 1, layer 2 is clear, and layer 3 is it a flattened layer?
No, layer 3 is still a convolutional layer.
Okay.
We
So
applied 40 filters, so we got 40 depth.
yeah. So for the output of layer 3, we are applying flatten.
Flatten, yes.
So that will become one dimensional.
It's going to
So it's a
be
very
49 to 49 into 40. That many number of 1600 1960 number of pixels will come there.
okay. That is then sent to
That is
that vector is sent to.
dense layer. Dense layer means the deep neural network.
So the fully connected 4 is actually a dense layer.
Dense layer. We call it as fully connected layer.
Okay.
Dense layer is
So,
called as fully connected layer.
so once we send that, what will happen over there? Is it applying the deep neural network?
Yeah, DNN. This is DNN. Till here it is CNN. Then you are applying DNN.
Mhm. So there also, can we specify all what we did in DLL, like the number of layers, or is it going to be a single layer?
This one, right? Yeah, we have to.
No, this layer 4 is only a single deep neural network.
Yeah, there will be, DNN means it will have the number of nodes, right? How many nodes you want? 100, 200? Each node will take, there will be 1960 weights for each node. It multiplies, and calculates linear combination, substitutes into the whatever activation function. The outcome is going to be passed to whatever the final node, right? Is that the question?
Yeah, that's right, sir. In the similar lines, but I'm just trying to visualize what will happen in the layer 4 fully connected.
It'll take a little while. You're actually thinking, in the class. I don't know how many are thinking, but it takes a little while to grasp it, and practice is the best way to grasp it all. Okay. So it
Okay, for
takes
now,
some.
can I assume like this fully connected one is actually a deep neural network?
No need to assume it is a deep neural network. It is a deep neural network.
Okay.
It is a deep neural network. We are combining CNN and DN. Why can't we use CNN as the last layer? Yes, we can. I'll show that also. That is called as fully convolutional neural network. That is, there is an advantage of it with that, and in object detection it is useful. I'll show that.
But these all 1960 are the values, inputs, something like
Inputs,
X1,
reduced
X1 and X.
dimensionality inputs.
Okay. So So those are all
That's
H1 to X1960.
Yes, yes, sir.
Okay, sir. Got it.
Okay then. So let me show you a bit of code here. Yeah, this is the neural network. So I have taken this same data set, right? I converted to categorical. We have already seen that. And now I reshaped the image into a three-dimensional matrix. 28 by 28 by 1, only one channel, 28 by 28 by 1. Because convolutional neural networks takes the three-dimensional arrays. And then I have taken the sequential class. I have taken the model that add, and then Keras layers on 2D, and then input shape, activation function, it filters, and kernel size stride is equal to 1. Right? These are all hyperparameters we have seen just now, right? And then second layer I added, third layer, fourth layer. We need to be careful while adding these layers, right? How much it is getting damaged. So n minus f plus 1, right? N minus f plus 1 means 28 minus 3 is 25 plus 1, 26 it became. 26 minus 5, 21 plus 1, 22 it became. 22 minus 7 is 15 plus 1, 16 it became. 16 by 16. 16 minus 9 is 7 plus 1, 8 by 8. It became 8 by 8 by 1. By the time it reached here, 64 pixels are there. 784 pixels I passed, and I got 64 pixels here. I flattened it and applied dense layers here and predicted it. That's how I actually experimented with that. Oh, sorry. Okay. So that's then we are flattening the outcome, because when you apply convolutional neural network, right, it is always going to give you three-dimensional array. When I flatten it, it becomes like x1, x2, x3 vector, and then I am passing it to dense layer. Right? This is the question you are asking, right, Seshram Garu? I am passing it to dense layer with 216 nodes. Right? Is this the question you are asking?
Yes, sir, that's right.
And then I am passing it to another dense layer, and then the final the prediction layer, soft dense layer. And rest is all same. We'll talk about this image generation and other things tomorrow, but rest is all same. So that is CNN neural network. Okay. So I'll stop here for today, because